Hello everyone, welcome back to another video in Stat385. So in this video, we'll be discussing comparison operators, a collection of operators that will become a little bit more clear as we go through it with some very quick examples, and then Boolean operators, which, again, you may be familiar with, but they perform operations on logical vectors. And finally, we'll dive into logical subsetting to show how a combination of comparison operators and Boolean operators can yield subsetting in data sets to extract more interesting smaller data sets for use in some sort of analysis, which we won't do data analysis in the class. So this will also sort of follow up on last week's lab, in which we did this as more of a demonstration. Okay, so first of all, comparison operators. So as these symbols suggest, we can check whether or not 3 is less than 9, and then it returns whether or not that is true. Okay, so, or 3 greater than 9. Oops. Okay, false. 3 less than or equal to 9. True. 3 less than or equal to 3. True. Okay, good. And 3 greater than or equal to 9. False. And here is 1. Okay, so 3. What this checks is whether or not the two objects under consideration are in fact equal to each other. So note that a single equal sign would do something like assign an object to a name stored in our global environment. This is the logical operator dictating whether or not two things are in fact the same. So if I go to 3 double equal sign 3, I get true. 3 double equal sign 9, I get false, so forth and so on. Okay. 3, this is not equal. So is 3 not equal to 9? In fact, it is not. Is 3 not equal to 3? False. Okay, and then we'll get into some of these in a little bit more detail, but I want to first refer us to the documentation, comparison. Okay, so we have our list of relational operators here, and we can extend these to vectors, which we will do in a little bit in this lecture, so you can see the documentation for this. Okay, great. Okay, so we can also do the same things for statements like this. True, less than or equal to false. Okay, so it says false, but however, if I do this, it says true. Okay, so what's going on here? So in this case, what we have is some type coercion. So if you recall, when we use mathematical evaluations, true gets converted to 1 and false gets converted to 0. So we have 1 less than 0, and that's why it returns false. Okay, so we have to be a little bit careful, but this this type coercion into a numeric type will be useful when we do some subsetting type things. Okay, so we also can do these little comparative operators for character vectors. This is not something that happens very often. We see that foo is less than bar, false, foo greater than bar, true. So we're not going to get into the details as to why one of these is true or one of these is false, but it requires some lexicographical ordering. In this case, the letter F comes after the letter B, but it's not something that comes up too often. But it's nice to know that we can, in fact, do these things. Okay, so continuing on. So now let's get a vector of, I'm going to do x equals sample 1 through 10, size equals 20. So I'm going to just draw the elements 1 through 10 a set number of times. Since the size the output that I want is 20 and the numbers range from 1 to 10. I should specify replace equals true. And we'll do the same thing here. Okay, so x, y. So this is going to do, so sample, as you've seen sample before, but just recall that what it's doing is it's doing random draws from the vector here. In this case, the vector is the integer vector from 1 to 10. And we're going to do 20 draws, and we're going to replace, as soon as we make a draw, we're going to put it back into the pile, and then for potential to be drawn again. So this is done randomly. So then another call to the sample function will do another random draw, so that x and y are not in fact the same. Well, let's check. Does x equal y? Okay, so what we can see here is that this is doing the checking for equality operation element-wise. And so we can see that, for instance, x, the first element of x is not equal to the first element y, so forth and so on. And we get only one case where they are in fact the same. So we can check, performing this operation element-wise, x greater than y, x greater than or equal to y, x less than y, and x less than or equal to y. Okay, so where this gets more useful and getting into some logical subsetting is we can, I don't want to go all the way down. If I do this, then I'm extracting the elements of x such that x is greater than y. So x greater than y, as we can see here, returns a logical vector. So that's going to obtain the locations in x where this condition is satisfied, and I can pull those elements out. Similarly, I can pull out the elements from y. And if we check these, yeah, we do see that that's the case. Similarly, I could do, and just kind of, okay, so x, so this is the case in x where x is less than or equal to y, and this is the case in y where that condition is satisfied as well. And so you can see that when we check x and y, we're looking for values where y is greater than or equal to x, so we do see 8 and 3 here, 3 and 4. Okay, so we do have, wait, what? Oh, sorry. Yeah, okay, so we do, okay, so x less than or equal to y. So we have a 3, 3, 2, 2, 6, 1, so forth, 8, 4. So these values are in fact all in y, all equal to x. And then when we look at x, we can see 3, 8, so forth and so on. We get the values themselves. Okay, great. Yeah, 4. Oh, okay, yeah, sorry, I was getting confused. So 3, 4, 3, 4, there it is. Okay, it's a little bit embarrassing. Okay, all right, so, right, these things, pulling some code from a source. These things do recycle. If I take the vectors 1 through 10, and I compare it to a vector of 8 and pi. So this is length 10, this is length 2. The lengths are multiples of each other. This will do valid recycling. So the first out, so this is 1. So the numbers range from 1 to 10, and then the first comparison is 1 to 8. Second comparison is 2 to pi. Then it's 3 to 8, 4 to pi, and that's when we get the first true. The recycling stuff in this is not, doesn't come up all the time, but we can do it. Okay, so one more thing. If I consider a logical vector, just kind of a throwaway logical vector, so what's going to happen here? So we have this comparison operator. We have a double over here, a logical over here. So to do the comparison, there's type coercion, so that this can convert to a 1 and 0 and 0. So we get true, false, false. Okay, so important to keep in mind what's going on with coercion and everything. Okay, so just because it requires, let's revisit this versus this again. So remember, this is a comparison operator between two objects. And this is an assignment operator. So this will always complain when you're doing this kind of comparison phrasing with equals. This does not check for equality. This does, the double equality. So these are two, even though the syntax is very, very similar, one's one equality and the other is two equalities, these things are completely different operations. So make sure that this is something that, if you're not careful, will cause a great amount of confusion. Okay, so here's some, unfortunately, tricky cases where we can get into some additional problems. Is where we have one, the double, and one, the integer, and they are true. But however, if I were to get into another function, which we've mentioned above here, if I supply 1 and 1L, now suddenly they're false. This is checking whether or not they are identical objects, and we can read the documentation to see what that means. Okay, so test objects for exact equality. Okay. However, if I were to what happens if I do all dot equal 1, 1L? True. Okay, so identical and equal are not exactly the same, are they? So this test if two objects are nearly equal, and then you can read the documentation for what that means. And we'll get into a little bit more details of that. Okay, so one more tricky example that is not meant to be a strange gotcha is this. Okay, so this is very confusing at first glance, right? We have 0 plus 1 plus 0.2, which clearly we can see because we can read is equal to 0.3. However, we have 0.3 on the right-hand side. They're not equal to each other. So what happened here? So recall that R is, R combined with your computer doesn't actually, read sentences. It's taking these quantities and it has some sort of floating point representation for each of the numbers on display. So you're not actually adding 0.1, you're adding some floating point based on, binary, like a floating point binary representation of this number, which is very, very close to this number, but maybe not exactly the same. And you're adding it to another floating point, like binary representation, and the resulting addition is not exactly the same. But however, they're very close. So if I were to go to identical and copy these things, we already know what's going to happen here because this is testing for exact equality, of which we just said that it wasn't. However, this approximate equality in all.equal will show that they are true. So all.equal admits some sort of floating point fudge factor to see if these things are, close enough. Okay, so this is, I know that this issue is very cumbersome and tedious and annoying and like challenging at first glance, but it is something that's very important because we cannot express real numbers on a computer. We just can't. So these kind of issues will flare up. Now, where they become important, so this is just, kind of a toy example that I know off the top of my head, but this comes up in, like math and statistics practice as well. Say you want to say you're studying like a square matrix and you want to find the null space. So you want to find the eigenvalues, which are 0 or something. So what is the difference between 0 and basically 0 according to a computer? Well, this is where you start getting into the differences between identical and all not equal. Maybe you're very, very, very close to 0, like 1e negative 34, which is equal to 0. And maybe that's a threshold that you would be satisfied with. If you're below some really, really small, close to 0 number, you can just call it 0. But anyways, it is an issue that is something you have to think about when you're doing that. And this is also a statistical issue as well, finding null spaces of matrices. Okay, anyways, that's getting way into the weeds. We can just demonstrate this more directly. If I were to print 0.3 with, say, a bunch of digits, we do see that it is not equal to 0.3 due to the binary representation, the floating point arithmetic, so forth, so on. Okay. All right, so continuing on, we can do, okay, give me 1 second here. Okay, so where am I? Lost my train. We have one more comparative operator. Okay, so what I can do is look at a particular vector and see whether or not the elements of one vector are in that of another vector. Okay, so let's just run it. So what this is doing is it's checking for, first of all, whether or not 1 is in this larger vector, and then it goes to whether or not 2 is in this larger vector, and then whether or not 3 is in this larger vector. And then what's displayed is related to the size of this first vector. So you can see the true, false, true here because 1 and 3 are in this larger vector, but 2 is not. So if I increase the size of the vector without adding a 2 in it, then this isn't going to change the output at all until I add a 2. Okay, so this comes up quite a bit. I've used it for maybe finding the indices of a vector with states, and I want to find which states are in a region or something like that. Okay, so I would have, if I did Midwest, maybe Illinois, Indiana, so forth and so on, and then I want in a broader region. Okay. Okay, so on to Boolean operators. All right. So let's see here. If I were to borrow some code, so I'm going to look at 3 vectors, foo, bar, baz, all logical. Okay, and then I can use any, and what any is going to do is check whether or not any of the elements in the logical vector under study are true. And we can see that yes, yes, no, and that's what's returned. Okay, so that's very nice. And then all is kind of the opposite. It would only flag true if all of the elements are in fact true. Okay, and of course you can combine now. Say, so all bar is false because there are some falses in it, and if I want not all of the elements are true, then this will say this is negation of that quantity. Okay, so let's see here. So if I were to, let's see if we can build a truth table and display these elements. Okay, so I have, let's just come up with a new vector. True, true, false, false, y equals. So we're going to build this inside of a data frame. Okay. And then we're going to alternate true and false. Okay. we can do, let's see here. How about not x? Not x equals not x. Okay, so let me see what this outputs. Okay. Ooh, what happened? Oh, I already had something declared on the global environment. That's odd. Okay. Now what? Okay. And you know what? This is not the best idea to demonstrate this point, but I can actually do this. If I can actually give it names to show what the operators actually do and formulate it into a data set. So this, that complains. Let me see here. Data dot frame. Okay. Aha, check dot names. What is that? I'm pretty sure. Syntactically valid variable names. Okay, so this is probably not the best in the way of practice with the R programming language, but it allows us to give the name so that we can display what the operator does. Okay, great. All right, so we can see that the exclamation point does negate X. So not true is false, not true is false, so forth and so on. Okay, great, awesome. Okay, so now how about X and Y? Okay. And we'll just build this as we go. All right, so then this checks whether or not both of the elements in these vectors goes element-wise. It says whether or not they're both the same type, or sorry, the same value. So here, X and Y are both true, it's true. X is true, Y is false, false, false. And then X, oh, sorry, no. Oh, I was wrong. It's whether or not it requires both of them to be true. My bad. So it's is this condition true and is this condition true? So right, okay. So so it's not whether or not they're the same value. That would be the other comparison, the equality operator. Right. Okay. Okay. Sorry for the confusion. Okay, then we do X or Y equals X or Y. So this is if one or the other or both are true. So we can see true, 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 false, false, true. So those are all true, and then both are false in the last case, and so therefore false. Okay. And so these are all fairly common Boolean operators. There's one more that isn't used as often, I would say, and that is XOR. And this is more in line with the word or, if you've ever seen the sentence and/or. The word or in that case would be if one of the cases are true but not both, or one of the objects under comparison are true but not both. And you can see what it's doing here. So XOR in this column, well, X is false, or X is true, Y is true. They're both true, so this flag's false. And then in the next two rows, we can see that one of the elements, either X or Y, is true, but the other is false, and therefore these are where the trues are returned. And then the last one, they're both false. Okay, so, right, okay, so pretty cool that we can demonstrate what this operator does inside of a data frame. So like inside of R, we can have a tabulation of what these things are doing, building a truth table. However, we did sort of have to cheat in the way of to use these nice variable names for this demonstration. We had to override what R views as synthetically valid. Anyways, that's gonna happen. Okay, so great. Okay, so we went through here. Let's do X and, okay, actually let's return. So we have X, we have Y. So this, what? Okay. Oh, this must be a new thing in the version. Give me one second to see. Okay, so let me see. Oh, you know what? Let's do something else here. We'll call it x1 equals true, y1 equals true. Okay, so previously this was shorthand for checking the first element in vectors. And so it looks like in the newer version of R, this is only now appropriate for length 1 vectors. Okay. So I'm guessing it's the same thing here. Oh, wait. Jeez, I'm being silly. Okay, true, yeah. So now it's only working with length 1 vectors. Okay, well, things change as R changes its versions. Okay, so this is doing and for length 1 vectors, and this is doing or for length 1 vectors. I'm sure that the reasons for this are in terms of computational performance under the hood. Okay, so let's go back to our vectors x and y, which not x, which y, and which not y. Okay, so what this is doing is it's pulling, if you could guess, based on what x is, which you can sort of see in the global environment there, it's extracting the elements that are true, or the indices of the elements which are true inside of the vector. This negates it. So remember our truth table, should be 3, 4, which y, this should be 1, 3, and this should be 2, 4. Okay, great. And these which things are pretty useful and used quite a bit. Okay, we could also do, and I'm sorry to just overwrite stuff, but let's do something like, what did we do above? Sample. You know what, actually I don't want to do sample. I want to do, so this is going to just draw real numbers. I say real because it's floating point in arithmetic. Between 0 and 1, we will do 20 of them. Okay, so we know that there is a maximum value in here. Let's find where it is. Which dot max. Okay, so it's the 17th element is the maximum. Okay, does that track? Just kind of looking at it, so 17, 19, 18, 17. Well, that's pretty close to 1. Looks right. Okay. You could also, okay, yeah. And then similarly, which dot min pulls the location of the minimum. Wow, they're right next to each other. Cool. All right, great. All right, so we have some Boolean operators, some fun functions for extracting of indices. Now, logical subsetting. All right, so let's see here. Let's take x equals, continue with this uniform thing. I'm sorry to just constantly be overriding things in the global environment. It's not the best practice, but for this demonstration, we're giving throwaway names or throwaway variable names. So bear with it. But apologies for constantly overriding things. Okay, so let's do x is 100 uniform draws between 0 and 1, with a little bit of rounding so that we can get something a little bit more manageable to work with. Okay, so then one thing you may want to do is say get all of the values of x between a given range. So, but R doesn't let you do this. So what you can do here is this is a logical comparison that makes sense. And this is a logical comparison that makes sense. Okay, so now say you want the proportion between the 0 point. So I make 100 draws of approximately uniform because there's some rounding, and I want the proportion of draws that are between this range. So all I have right now is a logical vector. How do I get what I want? Well, if I were to take my logical vector, just to emphasize the point, this is the logical vector, and I add 0, well, I get type coercion, right? It's going to convert it to double. And so now I have 1s when it's true, 0s when it's false. So if I want to convert that to a proportion, I can just use the mean. So I get logical, and then because I'm applying this function here for type numeric, type double, mode numeric, then it's going to do the type conversion and extract the proportion that I want, 0.18. And if you know some mathematical statistics, you can see that, well, if I take 100 random draws from a uniform between 0 and 1, round them, I should get about, my range is 0.2, so this proportion should be about 0.2, and it's pretty close. If I ramp it up, oh, that was bad. Too much ramping, that was slow. It gets pretty close. Okay, if I remove the rounding and do a little bit less ramping up, then very, very close. Yeah, the rounding caused a lot of problems there. Okay, great, awesome. All right, so then this is getting into stuff that we saw in the last lab assignment. So here I have a data set. We can view it. This is just, actually, so I didn't load in any packages. So in the lab, we loaded in a package for a data set that I guess is more interesting to people, the NFL data set. Here, this is a data set that's just in, I guess, base R and data sets. And what it has is air quality measurements in New York, May to September 1973. Perhaps this is interesting to somebody. It's not that interesting to me. But nonetheless, we can see that it is a real data set. It's still, it's only a few variables. There's some missing values. We get, what is it, 153 rows, 6 columns. Okay, great. So then, say we wanted something like the temperature, is it temp? Between, I don't know, how about 65 and 75 degrees. It's a pretty nice range, I guess. Okay. 65 less than 75. All right, so again, I have a logical vector. So these elements are true whenever the temperature is greater than 65. These elements are true whenever the temperature is less than 75. So these values are true whenever the temperature is between 65 and 75. And I can call this between temp, assign it, see it in the global environment, great. And so now I have air quality. I have a smaller data frame now where I'm looking at observations where the temperature is between 65 and 75. Great. Okay, great. So we can see how we can get to smaller data sets via this logical subsetting. Now, of course, okay, actually, let's just demonstrate one more thing. If I do OR here, it's gonna be a lot bigger. It's all of them. Why so? You can think about it and see. Okay, so anyways. Okay, so I'm starting to ramble on. Okay, so some points to highlight. This type of thing right here, the proportion of elements that are between some range for numeric variables is something that happens quite a bit in coding, so that this statement is very, very useful. And so let's just look at it one more time. So I have I'm gonna just ramp this down. Ramp it back down. Okay. Round. Okay, so what I'm doing here, okay, so this is this checks whether or not the element goes element-wise, whether or not x is greater than 0.5, and then we'll flag it true if that's the case. Whether or not x is less than 0.7, and it'll be a true if that's satisfied, and then the and gives you whether or not both cases are satisfied. Now, going down even a depth further, what's going on here, we have a vector of length 100 and a vector of length 1, and it's using length coercion so that it converts this to a vector of length 100, where the 0.5 is repeated 100 times. That's the length coercion that was used, and then the operator operates element-wise. Okay, so anyways, I have a vector of trues and falses, where the cases where the trues occur is when 0.5 is greater, or when the value is greater than 0.5 and less than 0.7. And then once I have that true false vector, and I supply that into a function mean, which works on numerics, I get type coercion. True gets coerced to a 1, false gets coerced to a 0, and then doing a mean of the 1 zeros gets the proportion of cases that satisfy the condition. Okay, so I'll end on that. All right, and I will see you next time. All right, take care. Bye.